Hi, let me start with week six discussion. Uh, I'm sharing my screen. Uh, Week six for Galois Theory. So in the notes, we have given some summary of results which have been proved in the class, and also to look at for time. Uh, this was also proved like when okay, let me check. Finite subgroups of unit group of a field, they are cyclic, right? This result has already been proved in some class. Okay. So for the proof, you just go through this. Uh, It is explained very well. Uh, there might be some little mistakes at at this point. It was just MI. Okay. Okay. So let's see. After this discussions, this is also used inside uh, some exercise. So remember the definition of roots of unity. Okay. Basically mu NL. Mu NL means nth roots of unity. Those which are solutions of x power n minus 1. This will be used in exercises, so remember that. And yeah, everything else is you just go through this and we'll see some exercises. Okay. Remember this result, Dedica and Artin result, which have already been discussed in the last session. So this is also important, might be used at some point, but I don't remember when it will be. I have seen these exercises. I hope we'll do this. Okay, let me start with first exercise. So we are given a group G which operates on X, which operates on X. G operates freely on X. Freely means if you have other than identity, it permutes all the elements, fixes no elements. Okay, that is for any X, sigma X is not equal to X. And same thing can be written as, okay, Z, I will write it like this. Z acts on X. This notation is for acts on. Z acts on X freely, or this action is free. Sigma belonging to G minus identity. Then sigma of X not equal to X for every X, right? The same thing can be written as if there exists X inside X such that uh, sigma of X is equal to X for sigma belonging to G, sigma is equal to identity. If some element is fixed by sigma, then sigma must be E. Okay. So they are same definition. So now we come to part A. What is part A saying? We have to show following statements are equivalent. So let's see. First implies second. How will we do? We know that G acts on X freely. Okay, we have to show for every x, we need to show, okay, we want to show that for any x inside x, this map g to x are given by sigma goes to sigma of x is injective. Okay, so how to do this? So let x belongs to x. We let fix x. Okay, let fix x belonging to x. Now we'll take this map. Let's say this is psi, then psi which depends on x. So better we should write x. Okay, psi x which is from g to x given by psi x of sigma is equal to sigma of x. Now we want to show psi is injective. Want to show psi x is injective or phi x is injective. Okay, so how we'll proceed it? As usual, showing map is injective. Psi of x of some sigma is equal to psi of x of some sigma prime. If these are equal, we'll show sigma is equal to sigma prime as element of C. Then this map is injective, right? Okay, so this is easy now because this will imply that sigma of x is equal to sigma prime of x, right? But this is our action, right? Gx acting on x. So if you act by sigma inverse from both sides, it will imply that sigma inverse uh, applied to sigma of x. This is sigma inverse sigma prime of x, but this is nothing but x because of definition of action. Okay, and now this will be saying because of definition of action only sigma inverse of sigma prime acting on x. Okay, and this implies sigma prime, sorry, sigma inverse sigma prime. This should be identity. Okay, this is from star definition by definition. Action is free. So, but this will imply sigma is equal to sigma prime. Okay, done. So psi is 1 1. Now we'll show 2 implies 3. Okay, what we have to show for any x g to gx, which is orbit of x, the same map which is sigma going to sigma x is bisective. Okay, we'll come. We'll show this. Let me first add more pages to my slide. Okay, let me check once if recording is been done or not. It is recording. Okay. So you can see also in YouTube. This PDF will be shared in description of that YouTube link, YouTube video. Okay. So if you are looking in YouTube, so you can find this PDF in description. Okay. Uh, we have to sort 2 implies 3. 2 implies 3 means we have to show given any x, the map G to Gx is bijective. Okay. Again, we have to show. First of all, what is this map? X is fixed. Let x belonging to x be. Let fix. Then, what is this map? First, we'll see this. Phi x from G to Gx, which is subset of x. This is same map. We are just restricting our codomain, right? So this map was already injective, if you remember. And it is surjective also, because now we are restricting our codomain to just this orbit of it. But anyway, we will show this because by default orbit is defined like G into X, where G is varying inside capital A. Okay, this is subset of X. Good. This map was injective. Now we want to show only surjective. Enough to show uh, injective is anyway true, right? How will you see this? Let's say G phi x of G. Let me prove this again. Phi x of G is equal to phi of, sorry, not here. Let me write in next page. Injective phi x of G is equal to phi x of G prime. Then this will imply Gx G prime x. Again, G inverse means acting by G inverse in this element. This will become G inverse G by x. Definition of x. G inverse G prime acting on x. But this is E into x, right? So, and this side we have G inverse G prime x. And this is x only. So, because now this man, because phi x is injective is was given. Okay, no need to write all of these things. Uh, okay, this is nothing but there if and all. Okay, by default, my phi x is defined like this. Okay, and this is if and only if G is equal to G prime by part A uh, using 2. So this is our injective. For surjective, we will what to do? Surjective. Any element of Gx, let some element y belongs to G dot x will show preimage through phi x. Then y is equal to G dot x for some G, right? Inside G. Now we got preimage of y is equal to G. Phi x of G will be G dot x and this will be y. This is this result was important because y belongs to Gx and this. So y will be of this one, G dot x. Okay, so this map is subject. Now 3 implies 1. And this was true for any x. Okay, these two things given any x belonging to capital X. Okay, this is true for any x. Full conclusion. Now 3 will imply first how G is acting on x. It is already given. We have to show action is free. Okay, that is we have to show if sigma belonging to G and sigma fixes some x for some x, then sigma should be identity. Okay, no other element fixes anything. Okay, good. Now for some x, okay, this is given. Okay, we'll assume this and we'll show this. So sigma fixes some x. So consider this. Consider phi of x. Okay, this x. Okay, so this is completely different than this. Here, something is true for every x, but this is we are fixing. If sigma fixes some element x, then sigma is identity. Consider phi x. What phi x do? Phi x is map which is bijective, which is bijective from third. We are using third this time. Now, where and sigma x is equal to x implies phi x of sigma is equal to, and this is e into x, no? Right? This can be written as phi of x applied to e. But because phi x is bijective, this will imply this step where we conclude that sigma is equal to identity. So action is free. Okay, I hope you understood. If you don't understood, you can ask me through the comments. Okay. Okay, so let's see second part, which is B. V be a vector space over infinite field K. G be subset of GLKV, which is odd KV, is automorphism group of B with K linear automorphism, which are K linear automorphism. If finite subgroup, this finite subgroup, okay, for the natural operation, G acts on X. Sorry, G acts on B, right? Because G is subset of automorphism group of B. Okay. So that there exists X inside V for which Gx means stabilizer of X equal to identity of V, which is uh, identity of group G also. So only stabilizer is trivial subgroup of G. That is what we need to show. Okay. So let's see B part. Um, K, infinite field, and G is the set of odd V, K, V is finite dimensional also. Okay, so let's see how to do this. Uh, K is infinite field and G is G is subset of automorphism group of V, where V is finite dimensional. A vector space. Over K. Then also an order of G is finite. We are considering action of G on X. G. Okay, let me write it next line. G naturally acts on V, and this G cross V2, we map G comma X. This goes to G of X because G is automorphism of V. So this is our action. It naturally acts on V. Now we want to show there exists one element in X which have a stabilizer X, trivial X stabilizer. What is a stabilizer? First, let's recall this. Cx is those elements of G which fixes X. Okay. G of X. This is also written like G dot X, whatever you prefer to write. Okay. Those elements of G which fixes X. This is our stabilizer. This name is stabilizer only. Now, what we want to do, note that this is subgroup of G because identity anyway belongs to this. Identity fixes everything. So in particular, it fixes X. And if G fixes X, H fixes X, so HG of X is also X. Okay, because by default, action of G is kind of associated. Okay, so first Gx, then Hx, or HGX together, they are same. Okay, let me write this. Okay, G dot X dot H. This is same as SG of dot X. Once this is H of X because G fixes, and H of X because H also fixes, so this is X. So HG also belongs to this. Right, HG belongs to GX. Okay, so And this one is by definition of action. You can prove this. This is a subgroup of G. Now we have to show there exists some element of vector space V for which stabilizer is only identity. No other element fixes. No other element of G fixes X. Okay. How will we do? Because G is finite, let's write G is equal to G1, which is identity, G2, Gk. Okay. This is our G. Uh, consider this set. Consider the collection of subspaces. Consider the subspaces. WGI, which is those elements of V, those vectors which are fixed by G. Gi of X is equal to X. Okay. And this is subspace of V. I from 1 to K. Note, note that WE is WE means WG1 is whole V, right? Understood? Uh, this is just because identity fixes all the elements of V. Okay. Uh, okay. So other than identity, will collect this union of WI, WG, I bigger than or I from 2 to A. This is proper subspace of V. How will we do this? First of all, what about let's have some rough work here. WG2. What is WG2? Because G2 is not identity. G2 will not fix something, right? Only identity fixes everything. If G2 also fixes everything, so what will happen? WG is proper subspace. How? Uh, WG is proper. Why? Because if G2, sorry, G2x is equal to x for every x in V, then this can be written as G2x is equal to E dot x for every x in V, right? Now, G2 is an automorphism, right? G2 is uh, G2 is an automorphism of V, and it fixes everything. This will imply G2 is equal to, okay? When two maps are equal, G2 is one automorphism, one automorphism of V. E is also automorphism of V, and T2 and E both are different in the collection where this is set, okay? Not repeating elements is written Gi not equal to Gi. So, but this is not a reason. So there exists some X where G2 does not fixes that. So this is proper. Similarly, all W since all WGI are proper subspaces of V. So here union does not cover. So this union is also proper. Okay. There exists X inside V minus union of WGX I from 2 to K. This implies GI of X is not equal to, sorry, X for every I from 2 to K. This implies only identifixes. Only EX is equal to X. This implies G of this X, GX is equal to E, which is the identity of it. All WIs are proper. This is just our justification for WG2, why WG2 is proper. Okay, good. Even G2 are different maps, then they should disagree at some point. G2 and E2 are here matching, then G2 should be equal to E. That is contradiction. That's how we shown WG2 is proper. And similarly, WK is also proper because WK is not WE. Then their union will not cover V. This also requires a proof why their union will not cover V. Okay, so that is different. Okay, this part let me check. For example, in R2, proper subspaces are lines and this point only. Okay, so finitely many lines will not cover R2, right? Finitely many lines does not cover R2. That is to understood, but it requires a proof. So check it. Okay, so part B is also, I hope you're clear with this. We'll go to some other problem. 6.2. Okay, in the 6.2 part is asking there exists a prime number P such that characteristic of L, characteristic of K, they are same equal to P, and Q will be power of P, okay, where Q is the order of L. Okay, how will we do? L is finite and K is its prime field means and L is containing K and K is the smallest. Where K is the smallest field. The smallest subfield in L. This is given because L is finite and 1 belongs to L. What will happen? What do you think? Uh, some n, which is adding 1 plus n times, will be equal to again 1, or what should I say? Repetition, because this is finite. It cannot go different. It cannot have different in infinitely many different types, right? So if you add n times it, you add n plus 1 times and so on. Some repetition will happen. Okay, that is, I'm writing n into 1. So will be equal to some. Okay, this is our definition. This is our identity element. Now, what to write here? Since L is finite, n into 1 is equal to n prime into 1, right? Some repetition will be happening, but this will imply that n minus n prime into 1 after cancelling, if n is bigger than n prime, then this will be equal to 0. Now, because we are in, since now we are in domain, right? L is field. L field implies n minus n prime into 1 is equal to 0. Implies n minus n prime is equal to 0. Because 1 is not 0. 1 is muted. Okay, but what is this? This is some number, right? This is some integer. Okay, so consider smallest. Okay, what is characteristic? Characteristic of L is, this is smallest integer. Smallest integer uh, or smallest natural number. Let me write here. Such that n into 1 of L, this would be 0, right? So this is existence of some m where m into 1 is will be equal to 0, but we should take a smallest integer n, then n will be characteristic. Okay, good. Uh, Now why it should be prime? Let's say this. Take natural morphism from Z to L, okay, where 1 is going to 1 of L. Understood? Then uh, what is kernel, right? Let's say this is our phi ring homomorphism or algebra homomorphism, Z algebra homomorphism. Then we have uh, by first homomorphism theorem of ring homomorphism theorem, Z modulo kernel phi inclusion into L. Okay. And also note that kernel phi is some ideal. So it should be of NZ type, and N will be the generator of kernel. Okay. Where N is smallest integer. I'm writing plus the positive integer, smallest positive integer. Okay. Okay. This I should write in front of us. Front of you. Front of such that N into 1 L is equal to 0 because this N belongs to kernel and it is also generator of kernel phi. So and N is smallest. So this implies N is N is also characteristic of L. This is N. Why N should be prime? That is our claim. Question is why N is prime? Because Z mod NZ is included in L, and L is domain. L field implies L is domain, implies Z mod NZ is also domain. Because Z mod NZ is sitting inside L. Also a domain when it is integral domain. This implies N should be prime. N is prime. N should be bigger than 1. Okay, so no chance of Z sitting inside L because Z is infinite and L is finite. So it is Z mod NZ where N is positive, and it should be prime because Z mod NZ should be integral domain. Good. So at least we have some characteristic. Oh, this much description for characteristic. Okay, no worries. So Z mod NZ is sitting inside L, and Z mod NZ is also field because N is positive prime. So this is some kind of ZP. Okay, I'm writing for N is equal to P now. So this is ZP sitting in L. So prime field K is ZP is the smallest field in L. This implies K is equal to ZP. So this ZP is smallest. This is prime field inside L. So, but anyway, now because L is finite, so L is finite dimension. This will imply L is finite dimensional vector space over ZP. Okay, and this will imply, let's say, x1, x2, if xk, or let me write in the notation in the form of notation. Okay, anyway, xk is basis of L over k, which is ZP, then order of L will be equal to order of linear span. This is, let's say, S, but linear span will contains how many? P choices for coefficients of this, P choices for coefficients of this is equal to P in Pk times product of Pk times. So this is detailed proof for this, where L over K is extension, which is also by default dimension of L over K. Not like this, dimension of L. Good. So this is also proved. Anyway, now part B. This took so much time, but it is not that difficult. Hint is given. You just understand it. So that L, which is zero set of x cube minus x, reduce that polynomial x cube minus x splits into linear factors. Okay, how will you do? Note that order of L is equal to p power k. Okay, p power k is only also denoted as q. Okay, p power k is also sometimes noted as q. So we have to show L is equal to v m to show L is equal to x zero set of x cube minus x. So what about L star? This is proved in the class that L star is cyclic subgroup. Sorry, cyclic group, finite cyclic group. L star is cyclic group, so there exists some x whose or cyclic group of order q minus 1, right? Total order of L is q, and other than 0, every element is invertible. So L star is just of order q minus. So Lagrange theorem will imply Lagrange theorem of group theory implies given any x inside L star, x ka power q minus 1 is equal to 1, right? Q minus 1 order k inside q minus 1 order group. L star is group under multiplication. Every element satisfies x power order of group is equal to identity. Okay, so all the elements of x, so all elements of L star satisfies, that is all elements of L star satisfy x power q minus 1 is minus 1. This value. Okay. Now, if you add 0 also, so a factor of x will come in, right? So this implies L, every element of L is contained in 0 set of uh, x into x power q minus 1 minus 1. Okay. This is just v of x q minus, but this is equality. Why this is equal? What is order of v? Sorry, v of x x q minus x. This is less than or equal to q, because q degree polynomial in a field can have at most q roots. But this, what this inclusion implies? Inclusion implies q, which is order of L. Inclusion implies that this is inequality order of v x q minus x. But this is also less than or equal to, all of them should be equal, right? Once all of them is equal, so L is, this implies, this inclusion implies L is equal to V. So, and all of distinct element of L, they are of q many elements, and it has q many roots. So x minus x q minus x splits into linear factors with each x belonging to L as proved with multiplicity 1. Simple rule. As a simple. This is what we wanted to show, right? So this can be factors like this. Further deduce the Wilson theorem. Wilson theorem is now easy. So let's say f L is equal to ZP only, so which is k. Then x power p minus x, all the elements of ZP, they satisfy this equation. V of this is equal to ZP only. Okay. So if you take order of this, or but from the above we have factorization, right? X power p minus x is equal to x into the product x minus I bar I from 1 to p minus 1. Okay, simple factors with multiplicity 1. All of the elements subject we are coming. Okay, so from here, if you putting capital X is equal to 0 or evaluating both polynomial uh, at 0, what will we get? So first, let cancel x because there is factor x, right? But this will imply that x power p minus 1 minus 1 is equal to this product from I equal to 1 to p minus 1 x minus I. And these are all equations of mod p. Evaluating at 0 or 0 bar, whatever. This will be minus 1, which is equal to product of minus I from 1 to p minus 1 mod p. But what is this? P is uh, each odd prime. P odd prime. Of course, we don't want to prove p is equal to 2. Okay. That is trivial. Okay. A proof for that can be deduced in other ways, not like this. But that should also work. But I don't want to do that. Here, this will be minus 1 to the power. From 1 to p minus 1, this is even number, some even. And this is factor of I from 1 to p minus 1 mod p. But minus 1 to the power some even number, that will be, that does not matter. And this product is p minus 1 factorial. So p minus 1 factorial is equal to minus 1. It is also written congruent to. Okay, so we have done second question also. Let's see next. What is next question? Six point five. So how will we do this? P is prime number, Q is some p power m, and m is positive integer. E is element of FQ, field of order Q. Both equation x square plus y square is equal to a, x square minus y square is equal to a, have solution in EFQ. Okay, so there is this P is prime Okay. How will we do this? First part, we will show v of x square plus y square. This is known as. This is what we want, right? Sum x y such that x square plus y square minus a is equal to 0. So we want 0. We want that 0 set of this. We fq. Let me denote as L as usual. VL. So how to proceed? Consider fq to fq. So fq star to fq star. X goes to f power q minus 1 by 2. This is a homomorphism, right? Some element goes to some, because q minus 1 is even. So this is some integer. This is some. This belongs to natural. So this is algebra homomorphism. I'm just defining on. Oh, is this true? But this is group homomorphism. Okay. With dot. This is actually group homomorphism, because these are abelian groups. Now, what do you think about this homomorphism? What should be its kernel? This is on my phi. So we are interested in kernel phi. If some element x is a square, okay. Let me do the work here. If y is equal to y square is equal to x, then where x goes? X goes to x power q minus 1 by 2, which is also y square q minus 1 by 2, but this is y power q minus 1, but q minus y is an element of fq only. So to the power q minus 1, it will become 1. So when x is a square of something, this goes to 1. When x is a square in L, x goes to 1. So kernel of phi contains all square elements. Okay. If you remember, in the fourth week session, we had for a given group G, we had these two notions, G2 and 2G, right? So one of them was elements which are square. I don't remember which one, but there we also had taken product of all elements of G2. Then it was denoted as mu G, right? Mu G2, mu G, mu 2G, and there was a relation between them, some relation. Okay. There also we proved Wilson theorem, if you remember. when G was considered ZP and we had taken product of all elements, the product should be uh, minus 1 mod P, right? This one. Okay, so uh, that is important here. You can have that in mind. Is this exactly the kernel, or there are some elements outside the kernel? The kernel of phi contains all elements which are squares. If y is not square, sorry, when x is not square, so fq star square, this is contained in kernel phi, and this is also contained in fq star. This part, then fq star will be equal to kernel of phi, but okay, so we can reduce this to zp only. Okay, I'm just creating all those things. Assume uh, fq is equal to fp. Okay, so because if you find the root within zp, so why to find roots in fq? If you find in zp, that is enough. Understood? I mean, you want to find some root in L. So better if you saw roots, there are roots in K, so that's enough, right? Because roots in K will be in roots in L. K is prime field, ZP. So in place of FQ, you just write FP or ZP. Hmm? Then our calculation will be there. Okay. So now kernel of phi, I'm just writing, you just check it. Kernel of phi is nothing but fp star square. Those elements which are square, and index is fp star, index fp star square, which is kernel. This index is 2. So half elements are square. So using this, uh, those elements which are square, okay, their uh, cardinality is, I mean, this set x square, x belonging to zp star or fp star, whatever, uh, cardinality of this set is just p minus 1 by 2. Okay, this was your kernel. Good. So once this is p minus 1 by 2, and you remember 0 is also a square. 0 square is equal to 0. So this cardinality x square such that x belonging to zp, now x is anything, then this cardinality is equal to p minus 1 by 2 plus 1 because of 0, and this is p plus 1 by 2. What about cardinality of this a minus y square, y running in ZP. This is cardinality of only y is running now. So how many y square, different y square will come? From here, you just look into it. So different y is running over all ZP. Hmm? How many distinct y square will come? P minus 1 by 2. Sorry, P plus 1 by 2 from here. Right? Because this is on ZP, not in ZP star. So this is also P plus 1 by 2. Now, if you take union, yeah, if you take union of these two sets, how many elements you will get in the union? If all of them are distinct, if uh, x square not equal to a y minus y square for any x y in ZP, what will happen? Then union of first set, union of x square, x belonging to ZP with a minus y square, y belonging to ZP, because these elements are distinct, no matching happening. Every x square is different, a minus y square is also different, they are not matching. Then this union, cardinality of this union will be p minus 1, sorry, p plus 1, p plus 1 by 2 plus p plus 1 by 2 is equal to p plus 1, which is strictly bigger than p. But if you see this, these are subset of ZP. So this is contradiction. So there should be some x square from first set and from some a minus y square or some y, they should match. Okay, so there is something or some element in the intersection, in the common or in the intersection. X square belongs to a minus y square. So x square will be equal to some a minus y square. That's all. Okay, what about second part, for which p sums of squares x square plus y square are squares in FQ. So P is random, FQ is also corresponding to that. When x square plus y square is a square. See, from here, if you see, every element happens to be sum of square of it. But in FQ, not every element is a square, right? For example, in F3, take just F3 for example. This is part B. Yeah. In F3, what is happening? 0 square is 0, 1 square is 1, 2 square is also 1. 2 is not a square, but can be written as sums of squares from part A. So, of course, prime P should not be equal to 3. So this happens only if P is equal to. This is the case when P is equal to 2. In no other case, such thing happens. Okay. And the proof here, it is proof for every. Oh, sorry. Here we use this is true if P is not equal to 2. Okay. So the P is equal to 2 is different case, and that can be solved. This problem A can be solved for P is equal to 2 in different manner. Like, okay, so when P is equal to 2 is every element is a square. How? Uh, in ZP we have, okay. How to in this case every element itself is a square. This is the case for P is equal to 2. Is this true? X from 2 minus x power 2 the 4 minus x. This is let me write for ZP means Z2. It works for F4. It's every element is square. We are not worrying about 0 and 1. Other than 0 and 1, elements are 1, sorry, x plus 1 and x. Yeah, this is 0, 1, x, 1 plus x. Where this we have this relation, it's x square plus x is equal to 1, or x square plus x plus 1 is equal to 0. Then is x square 1 plus x square becomes 1 plus x whole square becomes x square plus 1. Yeah, square 1 plus x whole square becomes x square plus 2x means 0 plus 1. But this is nothing but minus x. Minus x is also plus x because 1 and minus 1 they are same in Z2. So square of 1 plus x square is x. So this is a square. What about 1 plus x? Now x square is just minus 1 minus x. This is also 1 plus x. So every element is square. 0 square is 0, 1 square is 1. So here we verified for Z2 for F2 Okay. In case of F2, every element is a square. This is also proves this. Okay. I don't remember how. Okay, so I'm just telling it, but you should verify. The other case can be denied by part A. If P is not equal to 2, then not all elements are square. So you can find such contradiction, counter them. If P is not congruent to 1, then either this or this has solution in F cube. P is not congruent to 1, 1, 4, then S is equal to minus 2 as solution. Okay, if P is not congruent to 1, this will imply minus 1 is not a square. Okay, so if 2 is also not a square, that is if x square is not equal to 2, then okay, so all of these calculation, I don't think they are taking FQ, but my proofs almost I'm giving for Q is equal to P. Okay, I'm not giving you general proof. This also I didn't give general proof. This I'm not giving also this proof of this, but yeah, minus 1 is not a square, so minus 1, legendary symbol of minus 1 or mod P. This is minus 1. So this is notation from number theory, which is given in uh, series, a course in arithmetic, series book, a course in arithmetic. Okay, the first or second page it is given when minus 1 is not a square in ZP. So its legendary symbol is minus 1. When 2 is also not a square, then legendary symbol of 2, this is also minus 1. And this is these together will imply legendary symbol of minus 2, which is minus 1 into minus 2. So it can be written minus 1, 2. But first one is minus 1 is not a square. This is from this part is from here. Okay. And if we assume this part, then we are getting minus 1 into minus, which becomes plus 1. This implies minus 2 is a square. Okay. This proof is not for FQ. I'm just writing it ZP. For general proof, look in some book or ask in the doubt session or ask to the professor. Okay. Okay. So let's see other parts. still we have time, so we can solve some more questions. Okay, so FQ is finite field with Q elements. N is some positive integer. In this exercise, we want to count irreducible polynomials of degree n, monic irreducible polynomial of degree n. How to count them? Okay, this is formula. Here you have a field FQ. In the top, you want to count for n, right? So let n degree extension FQn. In this extension, we want to count irreducible polynomial of degree n. So for any divisor m or any m plus that m divides n, we have intermediary fields, right? And irreducible polynomial, monic irreducible for, okay, what this shows, irreducible m, any f inside this, such that f okay, this gives us a field. For any divisor m, we have here intermediary subfield FQM. Okay. If f is divisor, sorry, f is polynomial of degree m and m divides n, then there was an exercise which you will be solving, which was printed in blue. I can show you. That is somewhere here. This exercise, m divides n, and this f has a 0 in FQN. F is a divisor of x for qn minus x. All three are equivalent, right? So any irreducible monic where m divides n, f divides this corresponds to x power qn minus x. This polynomial, right? Actually, not this extension. Over fp. This extension corresponds, and what this extension corresponds in this polynomial x q minus x, and this corresponds to this polynomial, and what this corresponds x, or any m degree polynomial corresponds to this. In fact, f. So actually, there are in many fields within Q power n, they are isomorphism. That's all right, but like inside a field, okay. So anyway, forget about that. If f is irreducible of degree m and m divides n, then f will divide x power qn minus x. This is given in the exercise. You might be solving this. Okay. From here, what you conclude? F is a divisor. How many divisors are such? Right? This should be your next step. Good. So we will count this irreducible polynomials of m, where m divides n. M is integer such that then f is set f such that f belongs to irreducible of degree m in fqx. This in this of degree of f in n. So this set is also same as f belonging to fqx such that f is dividing of q x. I'm just counting irreducible of degree m. F in fqx. Okay. So how many such irreducible? But they corresponds to intermediaries of hills, right? So they are just divisors of xq minus the x. How many divisors it has of degree m? Let's see the hint. Okay, this can be written as all the factors. Then we will count it. So from here, from this conclusion, f is factor of this. So factorization of this, what will happen? Factorization of this. For any m dividing n, okay, we will just write f, all those f, and f is varying in irreducibles of degree m, right? But we don't know explicitly about f. Still, we can have some data. Can't consider degree both sides, applying degree relation. This side is degree. This side degree is just qn, and the other side जितने polynomials इधर हैं, the polynomials inside this set into degree of f, which is m, and then we have to sum for different m dividing n. So m is varying. But from here, applying Mobius inversion formula, Mobius inversion formula. What we'll get? We'll get this side irreducible of degree n is equal to, and here we'll get Mobius function summation m dividing n Mobius of n this function goes to other side q to the power, and this becomes ny. Then this is just Mobius inversion of, you can check it. What's given in the classroom notes. In the exercise sheet also given Mobius inversion formula. Okay, so this is done. And the second part is trivial for this. If you have this, what is this called? Part B of 6.1. Part B, just to note, P, Q, N, this number is nothing but how many in n degree extension of FQ, how many primitive elements are there. So for a n degree polynomial, which is irreducible, which gives this extension, okay, every irreducible polynomial will have n distinct roots, right? N distinct roots, and that will give this extension. So you take other n degree irreducible polynomial, that will give another distinct set of n roots. Okay, there will be nothing in the transaction because of some Galois theory. Galois group acts on roots of the polynomials, and so if polynomial is distinct, so roots should be distinct because yeah, one root goes to other and the action is transitive. Okay, and for this we have uh, ZNH and Galois. So for those reasoning, so counting FQN is sorry PQN primitive elements. Okay, primitive elements are those elements for which generates field over FQ. These elements. So these are for one polynomial you have n distinct primitives. So this counting primitives, n distinct primitive means one polynomial is, so we should write n into e to the power of n, right? Yeah, this is the relation we have. Here one polynomial will give n distinct primitives. So this is the relation. From here you just conclude it. So in that case, what we had to show, so yeah, in this case we had shown this, right? Oh, Mobius inversion formula. There was some in the inversion formula. We should get 1 by n here. Is that so? Let me check. Yeah. Uh, where is this 0? Here it is written. Not F here. Why we are getting 1 by n? That's not clear. This is our q power n. So when we take inversion formula, it becomes irreducible of n is equal to, sorry. So because the inside function is m into irreducible, so this should be n into this number. Okay, I understood. Let me write there. So this degree is this. Inside function is this x fx type thing, right? So in outside it should we should get n into this number, cardinality of this. Now this will go down. This n, which is here, it goes down. 1 by, becomes 1 by. Okay? So yeah, this is n into 1 by n. Summation m divides mu of m q power n by n. So this n gets cancelled out and it becomes just pq of n summation. Now use inversion formula and get this one. Okay, from inversion formula. It will become q m is equal to summation mu m dividing n, and this is p q m. Yeah. Okay, so let's see some other questions if we have time. Okay, we'll change them. I should not, but anyway, we'll arrange the PDF. Not this one. Now 6.10. Okay, we'll Let's see how to solve this 6.10. Fq is a finite field with q element and f is a polynomial given polynomial. Degree of f is q minus 2. Find the number of distinct zeros of f in q other than 0. That is, we want to count this cardinality of this. Hint is given. F is fq to this linear function. We'll consider the circular matrix. And then this cardinality is nothing but q minus 1 minus rank of this matrix. Okay. This is once hint is given, it is not difficult that much if you see it. For a proof, consider the product of this matrix. So this is your matrix A0, A1, A2, AQ minus 2. Then next matrix is A1, A2, A3, and you will get 0 here. And in the last, you will get AQ minus 2, then A0, A1, and so on, AQ minus 3. This is your matrix. Multiply with this, let FQ be your, this FQ star be X1, sorry, X0, X1, and so on, ordered. Okay, that is why I'm numbering them. X1, X2, Q minus 2, right? Total Q minus 1 elements which are non-zero. So 0 to XQ minus 2. Now I'm just writing this matrix X0 power 0, which is just 1, X0 power 1, and so on, X0 power Q minus 2. Okay, so that if you multiply first row with first column, it will become your equation, right? And then x1 0, x1 1, and so on, x1, sorry, x1 1 here, x1 2 here, x1 0 here, like this. So in the last you have xq minus 2 or q minus 2, and then the next one is xq minus 2 power 0, and so on, and xq minus 2 power q minus 3. If you multiply them, what will happen? What will happen? First row, first column multiplication becomes f. F evaluated at x0, right? See the second, first column into sorry, first row and second column. What will happen? If you take x1 common out there, then it becomes fx1. Just check it. Okay. And in the second, if you take x2 common out there, oh, not x2 square, it just becomes fx2, like this, and so on. In the last, if you take xq minus 2, q minus 2 common, fxq minus 2, it becomes something like this. So here, you will get just if you multiply by one more x naught, then only you are getting your equation. So you should multiply by x naught inverse so that it becomes fx naught, and so on. So here you will get x naught minus 2 fx naught, like this, and so on, up to x naught q minus q minus 2 fx naught. So in the second, you will get this fx2. You just check it. second row with second column. Once you multiply them, it will become fx2. Now down to it, you will get x2 inverse fx2 and so on. Okay, something like that. Good. X minus q minus 3 fx2. And here you will get x2 fx2. Here you will get, sorry, it was fx1. And here you will get fx2 and then like this. Okay. Similarly here, what you see here is this. First column is fx naught into some 1 x naught inverse and so on, x naught minus q minus 2. Okay, this is your first column. The second column was fx1, and here you have x1, x1 is no, it's just x1. Here you have 1, here you have x1 inverse and so on. Then and so on. In the last you have fxq minus 2. Some here xq minus 2, q minus 2, and so on, xq minus 2, and in the last one. Okay, these are your columns. So what you can say about this matrix? That every column of determinant of let me write, this is a, this is x. A determinant of x is non-zero. So which xi's are 0? Zero. Ith column decided. I plus 1 of 0 of f. They don't take part in the range, right? These vectors correspond to range where base. Okay, let me write every column vector of x or column vectors of x form a basis which goes to which goes to fxi into some vector, some vi. Fxi is a constant pair. And these are also linearly independent, so no need to worry about that. But these constants matters. If fxi is equal to 0, okay, let me delete it. If fxi is equal to 0, then image a of ci is equal to 0. So X, sorry, Ci belongs to kernel of A. By rank nullity theorem, now if you see which xi goes to 0, they correspond to some column vector Ci of X. So rank nullity theorem says rank A plus nullity of A is equal to rank of, sorry, dimension of V, which is in our case Q minus 1 dimensional vector space. But nullity of A means those Ci means Ci forms a basis for the null space. And they correspond to one with Fxi, which are 0. So this is nothing but FVF. Okay? And here Xi's are non-zero, so VF without 0. Those zeros of F which are non-zero means roots of F with non-zero roots. Okay. This corresponds to this, and rank will go to other side. Q minus 1 minus rank. Okay, this is also done. I hope you understand this calculation. And we are almost having time, so I don't think I should do more, but I can solve one question if you wish, 6.7 or 6.9. Let's 6.7 this one. L be a field so that mu n L is finite cyclic group whose order divides n. Okay, mu n L is mu n L. This is just those x inside L such that x power n is equal to 1. Okay, mu n L is cyclic. This is subgroup of multiplicative group L star, finite subgroup, right? Why finite? So mu n L, this is contained in V of x power n minus. And because every element of mu n L satisfies this polynomial, and this polynomial has only finitely many roots, at most L, less than or equal to, right? So mu n L is finite, and mu n L is less than n also. Now what? It is cyclic because it is finite subgroup of mu n L is subgroup of L star, finite also implies cyclic finite. Okay, finite implies cyclic. Okay, and whose order divides n. Okay, every element of mu n L satisfies xn minus, sorry, power n becomes 1. But Lagrange theorem tells x power n is equal to 1. X belonging to mu n L implies Lagrange theorem x power order of mu n L is equal to 1. But this already satisfies x power n is equal to 1. This implies let's say it is primitive. Then this is the order. Order of X is mu NL, order of the group. But this is also satisfied. This implies order of X divides N. Okay. These two things, this and this. Order of X divides N because X power N is equal to. Okay, so from this we conclude part A. If characteristic of K is positive, then mu n P of L is mu n L. B part, mu n L is same as characteristic of K is equal to P, which is positive, mu n P of L. How to show this? This set is X belonging to L such that X power N is equal to 1. And this set is X belonging to L such that X power N P is equal to 1. This inclusion is obvious, right? If X power N is equal to 1, this will imply X power N in power P is equal to 1 power P equal to 1, right? So X power NP is 1. I can directly write X power NP is equal to 1. This implies X belongs to mu NP. So one side is clear. Now for the other side, what you understand here, we have X power P NP. Okay, let me write as we should write. If X belongs to mu NP L, then X power NP is equal to 1. We want to show X power N is equal to 1. Okay. But from here, what you understand? What is given in the hypothesis is not yet used. X power N power P is equal to 1. But you see, this is happening in since X belongs to F Q star or L star, right? Then only it's unit. In fact, it is unit from here. It is clear. L star, and L star is order of L star is Q minus 1, right? Or some P n minus 1. since order of L star is pk some power pk minus 1, we have GCD P and order L star equal to 1. This implies there exists T S such that in integers such that PT plus S order L star is equal to 1. This will imply from here we'll capture this x power n for p is equal to 1 implies x power n is or p into t is equal to 1. Okay, you 1 power t will be 1. Now this will imply, and now I'm changing my color here, and x ka power s into L star. This will be 1 because x belongs to L star and L star multiplicative group and by Lagrange theorem. This is by Lagrange. What we get, focus on that. More you can say from here because this is also x power L star power s power n, whatever you can multiply. Okay? It will be 1 because inside is 1. So x power n power p t into x power n s L star is equal to 1 because this is 1. So total x power n power, this is 1 is equal to 1 and plus x power n is equal to, and this implies x belongs to mu n. So this inclusion is also true. This is for mu n L inclusion mu n L. This is mu n L. Okay. So these two are the proof, and that's where I'm ending. It's almost time, and we'll see you next week. People are invited.